ideal transformer or no load condition. So see here, consider an ideal transformer at no load as shown in the figure. Okay, this is the ideal transformer with the no load condition. Here no load. Okay, see here at a no load on the secondary side, the secondary current is 0. This is the first point. At a no load, no current. Okay, the primary side draws a current I1 which is necessary to produce the flux in the core. This is a flux, this is flux, and this current magnetizing the core of the transformer. Therefore, this current is also called the magnetizing current, which is denoted by Im. Therefore, see here, this Im is called magnetizing current. Magnetizing current. Okay, as the transformer is ideal, so we are discussing about the ideal transformer. As a transformer is ideal, the winding resistance is 0. It is purely inductive in nature. So it is inductive in nature. Please note down this one. It is inductive in nature. Ideal transformer is an inductive in nature. Therefore, the magnetizing current, lags this supplied voltage. Okay, because of inductive nature, this magnetizing current Im lags the supply voltage V1, and due to this magnetizing current, flux is produced in the core of a transformer. Therefore, Im in phase with the flux phi. Im in phase with the flux phi. Therefore, this flux link with the primary winding and produces the primary induced EMF E1. Okay, and same flux will link with the secondary winding and it will induce secondary induced EMF E2. Okay, now according to Lenz's law, the induced EMF always opposes the cause of producing it. Note down, according to Lenz's law, the induced EMF always opposes the cause of producing it. In this case, this is V1. Due to V1 only, E1 and E2 induced in the primary and the secondary of the transformer. Okay, therefore this E1, therefore E1, this E1 is opposite to the E1 is opposes the V1 with equal magnitude, Similarly, this E2 secondary induced EMF, always this E2 is opposes the V1, but its magnitude is not equal to V1, because its magnitude is depends upon the total number of turns on the secondary side. Okay, these phasor relations are very important to draw the phasor diagram. So ideal transformer are under no load condition. Please note down, in ideal condition ideal transformer under no load condition behaves like a inductive. So therefore, the magnetizing current, see here the first one, magnetizing current lags the V1, note down this one, and then the magnetizing current is in phase with the flux, and this E1 is opposite to the V1 with equal magnitude, and then E2 is opposite to the V1, but its magnitude is not equal because its magnitude is depends upon the number of turns on the secondary side. Okay, now note down this one, this all points, the same points. As a transformer is ideal, I already mentioned, as a transformer is ideal, its a winding resistance is 0 and it is purely inductive in nature. Please note down this one. Magnetizing current Im lags the V1 by 90 degrees. Okay, so it is purely inductive in nature. The third point is Im, this Im produces an alternating flux phi. So both are in phase, and this flux link with the primary winding and producing the E1 and E2. Okay, this is E1 and this is E2 on primary and secondary. Now fifth point is, according to Lenz's law, the induced EMF always opposes the cause of producing it, which is nothing but supply voltage. Therefore, E1 and E2 are antiphase with V1. Okay, note down this point. Based on these points, I am going to draw the phasor diagram. So see here, first point, to draw the phasor diagram, the first point is I am in phase with, I am in phase with phi. Therefore, it will come like this. This is phi and this is Im. Both are in phase. Okay. Now the second point. The second point is this Im lags the V1 by 90 degrees. The second point is Im lags the V1 by 90 degrees. So see here, this is 90 degree. It will come V1 here. Okay, this is V1. This is V1. This is 90 degrees. 90 degrees lags. And the third point is this induced EMF E1. This induced EMF E1 opposes the V1. You know this one. E1 is opposes the V1 with equal in magnitude, so it will come here this side. This is E1. Similarly, fourth point, E2 also opposes the V1, so it will also come here, but different magnitude. Its magnitude depends upon the total number of turns. Okay, this is the phasor diagram of ideal transformer under no load condition. So for better understanding, I am showing another, this one. This is pi, so this is flux which is in phase with Im in phase with phi, and the V1 is see here, V1 Im lags the V1 with 90 degrees. This is 90 degree. Okay, 90 degrees. So third point, E1 is antiphase or opposes the V1. See here, it will come down here, E1 with equal magnitude. This one are same magnitude. And fourth one, E2 is also opposes the V1. See here, with a different magnitude, because its magnitude depends upon the number of turns on the secondary side. Okay, this is the basic concept of ideal transformer and ideal transformer on no load condition. Thank you.